Why is it impossible for the Voyagers to truly escape the solar system? Somewhere in space, far beyond the planets we know, far beyond where the sun's light arrives with enough intensity to illuminate a day, two small craft continue their unending journey. They are the Voyager 1 and Voyager 2 probes, launched in the year 1977, when humanity decided to send messengers to the cosmos with the hope that someone somewhere might find them. Decades ago, these spacecraft crossed the orbits of all the known planets. Years ago, they traversed what we call the heliopause, that invisible boundary where the solar wind loses its battle against the interstellar medium. And yet, here we are questioning something that seems to contradict everything we have been told about these historical missions. The question is simple, but its answer is profoundly unsettling. Have they really escaped the solar system? Or are we witnessing one of the greatest illusions of space exploration? Because it turns out that, despite all the headlines proclaiming their triumphant exit toward interstellar space, the Voyagers remain trapped. They are still prisoners in an invisible cage that extends much farther than anyone imagines. And when you understand the true dimensions of this cosmic prison, when you grasp the real extent of the sun's gravitational embrace, your perception of these heroic journeys will change forever. Welcome to Ciencia Nocturna, where we explore the mysteries of the universe as the night enfolds us. If you enjoy this type of content and want to keep discovering the most fascinating secrets of the cosmos, do not forget to subscribe to the channel. Today, we are going to dismantle one of the most repeated myths of the space age, and we will do it with patience, with data, and with the tranquility that great revelations deserve. Before continuing, I would love to know from what part of the world you are listening to us tonight. Leave it in the comments. Are you joining us from America, from Europe, or perhaps from some more distant corner of the planet? It is fascinating to think that while the Voyagers travel alone through space, we are connected here, sharing this exploration of knowledge. Let us think for a moment about what a journey of escape represents. When we launch something into space with the intention of having it leave our planet, we need to achieve what we call escape velocity. For Earth, that velocity is approximately 11 kilometers per second. Any object that surpasses that speed can free itself from Earth's gravitational pull and move away forever. The Voyagers surpassed that barrier a long time ago. But here is the first problem. Overcoming Earth's escape velocity does not mean overcoming the solar system's escape velocity. The Sun, that star that seems so distant when we look at the sky, has a gravitational reach that defies imagination. Its mass is 330,000 times greater than that of Earth, and that mass generates a gravitational well from which it is extraordinarily difficult to escape. To truly liberate yourself from the sun's influence from the approximate distance of Earth, you would need to travel at about 42 kilometers per second. The Voyagers, at their moment of maximum speed, barely skimmed 17 kilometers per second, less than half of what is required. But wait, you might say, the Voyagers are much farther away than Earth now. Surely at that distance the necessary velocity to escape is lower. And you would be partially correct. Escape velocity does decrease with distance, that is true. However, the speed of the Voyagers has also decreased. The Sun's gravity, although weak at those enormous distances, never stopped pulling on them, imperceptibly slowing them down with every passing second. It is a race the probes are destined to lose, a silent battle against a force that never sleeps, never tires, and never ever gives up. When NASA announced that Voyager 1 had entered interstellar space in the year 2012, the world celebrated. Headlines proclaimed that humanity had finally sent something beyond our cosmic neighborhood, but that celebration was based on a very specific, very convenient, and technically misleading definition of the solar system's boundary. The heliopause, that border which the Voyager crossed, is merely the place where the solar wind can no longer push against the interstellar medium. It is a magnetic boundary, a particle boundary, but it is in no way the gravitational boundary, the true frontier of the solar system, the point where the sun's gravity finally loses its absolute dominion, lies much, much farther away. And that is where our story becomes truly astonishing, because we are talking about distances that make the Voyager's current journey merely the first step in a walk that will last tens of thousands of years. We are talking about a region of space so vast, so populated with objects trapped by the sun, that it makes everything we know of the solar system seem insignificant by comparison. Tonight, we are going to explore every layer of this uncomfortable truth, to calculate, to compare, to visualize exactly what it means to be truly outside the solar system. And in the end, you will understand why the Voyagers, those brave mechanical explorers, are destined to remain as prisoners of the sun for a time that exceeds all recorded history of human civilization. Prepare for a calm yet revealing journey, because what you are about to discover will forever change your understanding of our place in the cosmos and how truly difficult it is to actually escape home. Imagine for a moment that you are asked to draw the solar system. You would probably trace a circle for the sun at the center. Then you would add the 8 planets in their corresponding orbits. Perhaps you would include the asteroid belt between Mars and Jupiter. And maybe, if you are meticulous, you would add the Kuiper belt past Neptune, that region where Pluto resides along with thousands of icy objects. And you would end your drawing there, convinced of having captured the complete essence of our cosmic neighborhood, but you would be leaving out 99% of the story, because it turns out that everything we know and call the solar system is merely a small bubble at the center of something immensely larger. The fundamental problem with our understanding of the solar system's boundary is that there are multiple ways to define where it ends. We could say it ends at the orbit of Neptune, the last major planet, located about 4,500,000,000 kilometers from the Sun. That definition would make sense from a classic planetary perspective. Or we could extend the boundary to the Kuiper belt, that region extending to approximately 7,500,000,000 kilometers, where the trans-Neptunian objects orbit in the icy gloom of deep space. But neither of these definitions captures the complete reality of the solar influence. The heliosphere is another popular candidate for defining our boundary. It is a gigantic bubble created by the solar wind, that constant stream of charged particles emanating from the sun at supersonic speeds. This bubble inflates against the interstellar medium like an invisible balloon, extending asymmetrically in different directions due to the sun's movement through the galaxy. In the direction of solar motion, the heliosphere is compressed to about 15 billion kilometers. In the opposite direction, it stretches, forming a tail that could extend up to 60 billion kilometers or more. It is inside this magnetic bubble where solar particles dominate, where the sun's magnetic field dictates the rules, where the direct influence of our star is tangibly felt. When Voyager 1 crossed the heliopause in August of the year 2012, followed by Voyager 2 in November of the year 2018, the instruments on board detected dramatic changes in their environment. The density of solar particles dropped abruptly, while the intensity of galactic cosmic rays increased significantly. The magnetic field changed orientation, indicating that the probes had entered a region where the interstellar medium predominated over the solar magnetic influence. It was a historic moment, without a doubt, because it marked the first time that human-made objects had crossed this invisible boundary. But here is the crucial detail that most people do not understand. Crossing the heliopause does not mean abandoning the solar system. The heliopause is simply the boundary where the solar wind can no longer maintain its pressure against the interstellar medium. It is a frontier of plasma and magnetic fields, not a gravitational frontier. The Voyagers entered interstellar space in the sense that they are no longer bathed in solar particles, but they remain absolutely under the sun's gravitational dominion. It is like swimming in the ocean. You can get so far from the coast that you no longer feel the waves breaking, but you are still in the water, you are still in the ocean. The Voyagers stopped feeling the waves of the solar wind, but they are still swimming in the gravitational ocean of our star. To truly understand where the solar system ends, we need to think in gravitational terms. Gravity, unlike the solar wind or magnetic fields, never stops abruptly. It decreases with the square of the distance, but technically extends to infinity. However, there is a practical point where the sun's gravity becomes so weak that other stars begin to exert comparable influences. That point, that true limit of solar dominion, is determined by the outermost region gravitationally bound to our star, the Oort cloud. The Oort cloud is a theoretical structure because we have never observed it directly, but its existence is supported by overwhelming evidence. It is a gigantic sphere of billions of cometary nuclei that completely surrounds the solar system, extending from approximately 2,000 times the Earth-Sun distance up to 100,000 times that distance. To put this into perspective, if Earth were 1 meter from the Sun on a scale model, the Oort cloud would extend from 2 kilometers up to 100 kilometers away. It is a structure so vast that its outer edge dangerously approaches half the distance to the nearest star, Proxima Centauri. These Oort cloud objects are gravitationally bound to the Sunday. They orbit our star over periods that can last millions of years, following extremely elongated trajectories. Occasionally, gravitational perturbations from nearby passing stars or galactic tides nudge some of these objects toward the inner solar system, where we see them appear as long-period comets. The existence of these comets is precisely the evidence that confirms the presence of this distant reservoir. And as long as these objects remain bound to the Sun, as long as they continue to orbit under its gravitational influence, they are part of the solar system by definition. The Voyagers have traveled approximately 160 times the Earth-Sun distance. It sounds impressive until you realize that the Oort cloud begins at about 2,000 times that distance. The probes have not even reached the entrance of the solar system's true gravitational boundary. They are in an intermediate zone, a space between the heliosphere and the Oort cloud that is technically interstellar in composition, but solar in gravitational affiliation. It is a cosmic limbo where definitions become blurred and where the truth is revealed in all its uncomfortable complexity. There is a place in space so vast and so populated that it contains more objects than all the planets, moons, asteroids, and comets of the inner solar system combined. A place so distant that the sun's light takes more than a year to reach it, where our star shines barely brighter than the others in the night sky. A place we have never visited, never photographed, and that we will probably never see directly in our lifetimes. And yet, this place defines the true size of the solar system and determines the ultimate fate of the Voyager probes. We are talking about the Oort cloud, the largest and least understood structure in our cosmic neighborhood. The story of the Oort cloud begins with a Dutch astronomer named Jan Oort, who in the year 1950 proposed its existence to explain a puzzling mystery. Astronomers had observed long-period comets, icy objects that appeared from seemingly random directions in space. They followed extremely elongated orbits around the Sun and then disappeared for thousands or millions of years. These comets did not come from the Kuiper belt, which is approximately flat and aligns with the plane of the planets. These comets arrived from every possible direction, suggesting a spherical origin that completely enveloped the solar system. Oort proposed the existence of a spherical cloud of cometary nuclei located at enormous distances from the Sun, where these objects would remain frozen for eons until some gravitational perturbation sent them toward the inner solar system. The theory was elegant, mathematically sound, and perfectly explained the observations. Over time, as we discovered more comets and refined our models, the evidence for the Oort cloud's existence became overwhelming, although we have never directly observed a single Oort cloud object in its original location. Its presence is as certain as the existence of Neptune was certain before it was directly observed, predicted solely by its gravitational effects. The dimensions of the Oort cloud defy all intuitive comprehension. It is estimated to begin approximately 2,000 astronomical units from the Sun, where 1 astronomical unit is the distance between Earth and the Sun, about 150 million kilometers. That means the inner edge of the Oort cloud is 300 billion kilometers away, 20 times farther than Neptune and 2,000 times farther than Earth. But that is just the beginning. The cloud extends outward up to approximately 100,000 astronomical units, or even up to 200,000, according to some models. We are talking about 15 trillion kilometers at its farthest extent, a distance equivalent to almost 2 light years. To put these figures into human perspective, consider the following. Light, traveling at 300,000 kilometers per second, takes 8 minutes to get from the Sun to Earth. It takes hours to reach Neptune, but to reach the outer edge of the Oort cloud, light needs almost 2 full years. The Voyagers, traveling at 17 kilometers per second, have been in space for almost 50 years and have barely covered 1/3 of 1% of the distance to the Oort cloud's inner edge. At their current speed, they will take approximately 300 years to reach that inner edge and another 30,000 years to traverse the cloud completely and emerge on the other side. The Oort cloud is not a uniform structure. Scientists divide it into 2 main regions, the inner cloud, or Hill's cloud, and the outer cloud. The inner cloud, extending from approximately 2,000 to 20,000 astronomical units, is shaped like a thick disk or torus and contains perhaps 5 times more mass than the outer cloud. The outer cloud, from 20,000 to 100,000 astronomical units or more, forms a more diffuse spherical distribution. This outer region is the source of the long-period comets we occasionally see, while the inner cloud is much more stable and rarely loses objects toward the inner solar system. How many objects populate this remote region? Estimates vary enormously, but models suggest there could be several trillion cometary nuclei, with diameters greater than 1 kilometer. The total mass of the Oort cloud is estimated to be approximately 5 times the mass of Earth, although this number is highly uncertain. These objects are primordial remnants of the solar system's formation, ejected into these distant orbits by gravitational encounters with the giant planets during the first millions of years of solar history. They are frozen time capsules, preserving the chemical composition of the original protoplanetary disk. The Oort cloud is also a humble reminder of how insignificant our presence is in the cosmos. Everything humanity has explored directly with spacecraft, every planet visited, every moon photographed, every asteroid studied, all of that occurs in a minuscule bubble at the center of this immense structure. It is as if we had meticulously explored a single room of a house without even knowing the existence of the rest of the building, the garden, or the neighborhood surrounding it. The Voyagers, our most distant explorers, have barely stepped out of that room into the hallway. And here is the crucial point. All these Oort cloud objects are gravitationally bound to the Sunday. They orbit our star over periods measured in millions of years, following trajectories that eventually bring them back. however imperceptibly. The Sun's gravity, although incredibly weak at those distances, is still sufficient to hold them captive. And if the Sun can hold billions of objects captive at distances of 1 or 2 light-years, then it certainly can hold captive 2 small spacecraft that have barely reached a minuscule fraction of that distance. The Oort cloud is not simply the boundary of the solar system, it is the living proof that escaping the Sun's gravitational embrace requires reaching distances that no human-made object will reach for tens of thousands of years. There is a persistent illusion in our everyday understanding of gravity. We tend to think of it as something that has a limited range, as if there is a distance after which it simply disappears and frees you. We see astronauts floating on the International Space Station and assume they have escaped Earth's gravity. We observe that the Voyagers have traveled beyond all the planets and conclude that they must be free from solar influence. But the reality is much more inflexible, much less generous. Gravity never lets go. Never. It simply weakens to the point of becoming imperceptible, but it never disappears completely. Newton's law of universal gravitation tells us that the gravitational force between 2 objects is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. This seemingly simple formula has profound implications. First, it means that as long as both objects have mass, a gravitational force will exist between them, no matter how far apart they are. Second, the inverse square term implies that the force decreases rapidly with distance, but never reaches zero. At infinite distances, the force approaches zero, but mathematically speaking, it never reaches it. This is the relentless nature of gravity. It is a chain that stretches until it becomes infinitely thin, but it never breaks. When we talk about escape velocity, we are talking about the minimum speed necessary for an object to move away indefinitely from a massive body, without the need for additional propulsion. For Earth, that velocity is 11.2 kilometers per second at the surface. For the Sun, from the distance of Earth's orbit, it is approximately 42 kilometers per second. These figures are not arbitrary. They are determined by the mass of the central body and the distance from which the escape begins. Escape velocity represents the point where the object's kinetic energy is exactly sufficient to counteract the gravitational potential energy that holds it bound. The Voyagers were launched with the help of powerful rockets and received additional gravitational boosts from their encounters with the giant planets. At its peak velocity, Voyager 1 reached approximately 17 kilometers per second. With respect to the Sunday Voyager 2 reached similar speeds. These are impressive velocities for human-made objects, fast enough to cross Earth's diameter in just over 12 minutes. However, these velocities are far below the 42 kilometers per second required to escape the solar system from Earth's orbit. Now, you could correctly argue that the Voyagers are no longer in Earth's orbit. They are much, much farther away, and escape velocity decreases with distance. At the Voyager's current distance, approximately 160 astronomical units from the Sun, the escape velocity has been significantly reduced. We can calculate it using the escape velocity formula adjusted for distance. At that distance, the necessary velocity to escape is approximately 3 kilometers per second. The Voyagers are traveling at 17 kilometers per second, so they are clearly above the local escape velocity, right? This is where the mathematics becomes brutally honest. The problem is that the Voyagers are not maintaining a constant speed of 17 kilometers per second. From the moment they left the gravitational boosts of the giant planets, they have been continuously decelerating due to solar gravity. It is a minuscule deceleration, imperceptible on human timescales, but it is real and cumulative. Every passing second, the Sun's gravity pulls them back, stealing an infinitesimal fraction of their speed. Over decades, these fractions add up. Over centuries, they become significant. Over millennia, they are determinant. What truly matters is not the Voyager's instantaneous velocity right now, but their total orbital energy. Orbital energy is the sum of kinetic energy and gravitational potential energy. An object with positive orbital energy can escape. An object with negative orbital energy is permanently bound. The Voyagers have negative orbital energy. They are on hyperbolic orbits around the Sun, which means their trajectories are open instead of closed, but they are still gravitational orbits. They are not falling back toward the Sun, but they are not truly escaping either. They are in an intermediate state, perpetually moving away, but always remaining under solar gravitational dominion. To understand this intuitively, imagine throwing a ball upward from Earth's surface. If you throw it with enough force, but below escape velocity, the ball will go higher and higher, gradually slowing down due to gravity. It will eventually reach a maximum point and begin to fall back down. Now imagine throwing the ball right at escape velocity. It will go up forever, constantly slowing down, but its velocity will never reach zero. The Voyagers are in a situation similar to this second ball, except their initial velocity was insufficient, even for this scenario. They are on a trajectory that will take them incredibly far, but the solar gravity will never let them go completely. The mathematics is clear and unforgiving. When we calculate the specific orbital energy of the Voyagers, which is the orbital energy divided by their mass, we get a negative value. This confirms that they are gravitationally bound to the solar system. They will continue moving away for tens of thousands of years, traversing the Oort cloud with glacial slowness, but they will technically remain in orbit around the Sunday. Their speed will decrease asymptotically, approaching some minimum value, but never completely stopping due to the Sun's movement through the galaxy and the gravitational perturbations of other stars. This is the uncomfortable truth that popular narratives prefer to ignore. The Voyagers have not escaped. They cannot escape. They were launched with insufficient speed to break the Sun's gravitational chains, and now they are condemned to remain as perpetual prisoners, moving away but never free, traveling but never arriving, exploring an exile that will last longer than entire civilizations, but which will never take them beyond the ultimate reach of the star that saw them born. 17 kilometers per second, 61,200 kilometers per hour, 1,469,600 kilometers per day. Numbers that sound impressive, speeds that defy everyday human comprehension. At that speed, you could travel from New York to Los Angeles in less than 3 minutes. You could circle Earth in just over 2 hours. You could reach the Moon in less than 6 hours, a fraction of the time it took the Apollo astronauts. And yet, when we talk about interstellar space, when we consider the distances involved in truly escaping the solar system, 17 kilometers per second is painfully, desperately slow. The Voyager probes achieved these speeds thanks to an extraordinary combination of engineering and planetary alignment. They were launched during an orbital window that occurs only once every 176 years, when the giant planets align in such a way as to allow what we call gravitational assist, or the gravity slingshot effect. Voyager 1 visited Jupiter and Saturn, using the gravity of each planet to accelerate and change its trajectory. Voyager 2 completed the Grand Tour, visiting the gas giants Jupiter, Saturn, Uranus, and Neptune. Each planetary encounter worked as a free boost, stealing a minuscule fraction of the planet's orbital momentum to accelerate the probe. When Voyager 2 left Neptune in August of 1989, it had reached its maximum speed with respect to the Sunday. It was the last boost it would receive, the last time the gravity of a massive object would accelerate it instead of slowing it down. Since that moment, Both Voyagers have been in freefall in the purest sense of the term, following trajectories determined solely by their initial velocity and the Sun's gravitational pull. And that pull, although weak, has never stopped acting upon them for a single second of the last 48 years. To truly appreciate how inadequate this velocity is for actual escape, we need to make some comparisons with comprehensible timescales. Voyager 1, the fastest and farthest of the two probes, is currently approximately 165 astronomical units from the Sunday. It has taken almost half a century to get there. Neptune is 30 astronomical units away. The heliopause, that boundary we celebrated so much when it was crossed, is at approximately 120 astronomical units in the direction of solar motion. The inner edge of the Oort cloud is at 2,000 astronomical units. The outer edge is at 100,000 astronomical units or more. Let us do the calculations. At 17 kilometers per second, maintaining constant speed, which is impossible due to gravitational deceleration, but let us assume it for simplicity, Voyager 1 would take approximately 300 years to reach the inner edge of the Oort cloud, and another 30,000 years to completely traverse the cloud and emerge on the other side. 30,000 years. To put it in perspective, 30,000 years ago, modern humans were just beginning to create the first cave paintings in Europe. The pyramids of Egypt would not be built until another 25,000 years later. The written history of humanity would not begin until another 28,000 years after that. The nearest star to our Sun is Proxima Centauri, located 0.2 light-years away, approximately 268,000 astronomical units. At Voyager 1's current speed, reaching Proxima Centauri would take approximately 73,000 years. But here is the cruel detail. Voyager 1 is not heading toward Proxima Centauri. It is heading toward a region of space in the constellation Ophiuchus. The nearest star in that direction is Gliese 545, located 17.6 light-years away. Reaching it will take approximately 400,000 years, assuming the Voyager's speed remained constant, which it will not due to the gravitational perturbations of other stars and the general motion of the galaxy. Voyager 2 is heading toward a different region of the sky, toward the constellations of Pavo and Telescopium. The nearest star on its path is Ross 248, located 10.3 light-years away. Reaching it will take approximately 300,000 years. But even when these probes pass near other stars in the distant future, they will not enter orbit around them. They will simply pass by as silent visitors in the night, too fast to be captured, but too slow to truly escape the gravitational dance of the galaxy. It is important to understand that these velocities, although impressive for human-made objects, are minuscule in cosmic terms. Earth orbits the Sun at approximately 30 kilometers per second. The Sun moves around the galactic center at 220 kilometers per second. Some stars in the galaxy have peculiar velocities of several hundred kilometers per second. The jets from supermassive black holes eject material at speeds close to that of light, 300,000 kilometers per second. In this context, the Voyagers are crawling at a cosmic tortoise's pace, barely moving in the grand scheme of the universe. And here is the final irony. Even if the Voyagers had been launched with double the speed, even with 30 kilometers per second, they would still need thousands of years to traverse the Oort cloud. Even at 100 kilometers per second, a speed completely unreachable with our current technology, they would still need several thousand years. The distances involved are so vast, so incomprehensibly enormous, that no reasonable, achievable speed with chemical or even nuclear propulsion would make a significant difference on the necessary timescales. The Voyagers are traveling at record speeds for human objects, but in the context of true solar system escape, they are essentially immobile. They are like ants walking toward the horizon, moving with all the speed their tiny legs can generate. But the horizon always remains just as distant, 17 kilometers per second toward nowhere, because nowhere is so far away that no achievable human speed will make the journey less than intergenerational, less than civilizational, less than epic, on scales that defy all human proportion. 30,000 years. Stop for a moment and truly consider what that number means. 30,000 years is more time than agriculture has existed. It is more time than we have had cities, writing, or civilization as we understand it. 30,000 years ago, our ancestors lived in caves, hunted mammoths, and were just beginning to develop the cave art that we admire today in places like Lascaux and Altamira. The very concept of written history would not exist for another 25,000 years after that. And yet, this is the minimum time the Voyager probes will need to completely traverse the Oort cloud and emerge on the other side, assuming they encounter no significant delays on their path. To better contextualize this figure, let us do a mental exercise. Imagine we could travel 30,000 years into the past. We would arrive at an unrecognizable world where Neanderthals still coexisted with modern humans in Europe. The continents had slightly different shapes due to sea levels during the last ice age. Megafauna walked the earth: giant ground sloths, saber-toothed tigers, short-faced bears that made modern grizzlies look small. No human-made structure from that era survives today. No name, no story, no individual memory has reached us from that distant time. It is a temporal abyss so profound that it erases all cultural continuity. Now, turn your gaze toward the future. In 30,000 years, when the Voyagers finally complete their transit through the Oort cloud, what will remain of our current civilization? Will humans still exist as we know them today? Will anyone remember these probes, their mission, or even the names of the people who built and launched them? The timescale involved transcends all human planning, all institutional purpose, all continuous cultural memory. We are talking about a journey that will last longer than empires, longer than languages, longer than probably the entire geopolitical configuration of planet Earth. The inner Oort cloud, also known as the Hills cloud, extends from approximately 2,000 to 20,000 astronomical units. This denser region will take the majority of the transit time. At the Voyager's current speed, crossing just this inner section will require approximately 10,000 years. It is as if the probes had been launched in the year 8000 BCE during the early Neolithic period and were only now reaching their intermediate destination. During that span, humanity went from hunting and gathering to agriculture, built the first cities, invented writing, developed complex civilizations, went through the Bronze and Iron Ages, and eventually reached the Space Age. The outer Oort cloud, less dense but much more extensive, will add another 20,000 years to the journey. This region extends from approximately 20,000 to 100,000 astronomical units, and in some models, up to 200,000 astronomical units. The diffuse nature of this region means that encounters with individual objects will be rare, but the vastness of the space that must be traversed compensates for this low density. The Voyagers will spend most of their journey in this zone, floating in near absolute darkness, where the sun is barely a bright star among many, without distinctive characteristics, except for its familiar position in the sky. Throughout this time, the probes will be completely dead in terms of functionality. Their radioisotope thermoelectric generators, which currently provide increasingly scarce power, will completely run out sometime in the decade of 2030. From that moment on, all communications will cease, all scientific instruments will fall into permanent silence. The Voyagers will continue their journey in absolute solitude, unable to observe, unable to record, unable to communicate anything they encounter. They will simply be inert objects moving through the vacuum, as silent and passive as the cometary nuclei that will surround them. But even after traversing the Oort cloud, even after those 30,000 years, the Voyagers will not have truly escaped. They will have left the region where physical objects orbit the Sun, correct? But they will still be under significant solar gravitational influence. The Sun's gravity at that distance will be comparable to the gravity of other nearby stars, but it will not be zero. They will be in a kind of gravitational no-man's land, where multiple stars exert similar influences and where galactic tides begin to dominate over individual stellar attractions. The truth is that defining an exact point where the solar system ends is arbitrary when we look at it from this temporal perspective. We could say it ends when solar gravity no longer dominates over the perturbations of other stars. We could say it ends when there are no longer objects bound in orbit. We could say it ends when an object finally reaches its first close approach to another star. Each definition yields a different answer, but all agree on one thing. The time required is measured in tens of thousands of years, not decades or centuries. The Voyagers were launched with great fanfare, celebrated as messengers of humanity to the stars. They carried golden records with sounds and images of Earth, designed to be found by alien civilizations in the distant future. But the reality of their journey is much less romantic and much more humbling. They will spend 30,000 years crawling through the Oort cloud, as trapped by the Sun as Earth itself is, only in a more elongated and distant orbit. The true farewell to the solar system is not an event we can witness or celebrate. It is a process so glacially slow that it transcends all human experience, all cultural time frame, all civilizational continuity. It is a reminder that the cosmos operates on scales that make our lives, our cultures, and our most grandiose ambitions seem insignificant. There is a future moment, not so distant in cosmic terms, when the Voyager's radio signals will simply cease to reach Earth. It will be an ordinary day in mission control, if a mission control still exists by then. The engineers, or their technological successors, will send their usual commands into deep space and receive no response. They will try again, adjust frequencies, check their equipment, but the truth will be inevitable. The probes will have used their last gasp of energy, transmitted their last signal, and entered an eternal silence from which they will never emerge. This moment approaches faster than many would like to admit, and represents not a technical failure, but the inevitable fulfillment of the destiny of all machines. The Voyagers do not run on conventional batteries or solar panels. At the distances they operate, sunlight is too weak to be useful, millions of times less intense than in Earth's orbit. Instead, each probe is equipped with 3 radioisotope thermoelectric generators, devices that convert the heat from the radioactive decay of plutonium-238 into electricity. When they were launched in 1977, these generators produced approximately 470 watts of electrical power. That is roughly the power of 5 old incandescent light bulbs, enough to power all the scientific instruments, the communication system, and the heaters that protect the electronic components from the extreme cold of space. But plutonium-238 has a half-life of 87.7 years, which means that approximately every 88 years, half of the radioactive material will have decayed into uranium-234 and molybdenum. This implies that the production of heat, and therefore electricity, inexorably decreases over time. It is not a sudden decline, but a gradual one, an exponential curve that becomes steeper with every passing decade. Currently, after almost 50 years in space, each Voyager's generators produce approximately 250 watts, little more than 1/2 of their original capacity. This continuous decrease has forced NASA engineers to make increasingly difficult decisions about which systems to keep active and which to permanently turn off. The first casualty was the heating system. As the available power decreased, engineers began to turn off heaters one by one, allowing different components to cool to temperatures for which they were never designed. Surprisingly, many instruments continued to function far beyond their minimum temperature specifications, operating at tens of degrees below zero when they should have failed long ago. It is a testament to the over-engineering and build quality of the 1970s era, when electronic components were manufactured with generous safety margins and robust materials. Then came the scientific instruments. Voyager 1's magnetometer was turned off, followed by several other instruments on both probes. Each shutdown was a small death, the permanent silencing of a sensor that had been observing the cosmos for decades. The plasma detection instruments continued to operate, as did the cosmic ray detectors and the communications system. But the list of active systems shortens year after year. It is like watching a loved one age, losing capabilities one by one, until only the most essential functions remain. Current projections suggest that by the year 2030 approximately, the available power will be so low that even the most basic systems cannot be maintained. Engineers will have to choose between maintaining the scientific instruments or maintaining the radio transmitter. Eventually, not even that choice will be possible. The power will drop below the minimum threshold necessary to transmit a detectable signal across billions of kilometers of empty space. The Voyagers will continue to orbit the Sun, continue to move away, but they will do so in complete silence, unable to tell us anything about what they encounter or experience. When that final moment arrives, there will probably be no ceremony or dramatic announcement. We will simply stop receiving signals. Perhaps we will try for weeks or months, sending commands in case it was only a temporary failure, but eventually we will accept the reality. The Voyagers will have died functionally, although physically they will continue to exist as inert objects floating in the darkness. Their aluminum structures will remain intact for millions of years. The golden records will remain attached to their sides, preserving sounds and images of an Earth that by then will have changed unrecognizably. It is strange to think that these probes will survive everything we know. They will survive their creators, NASA, probably human civilization in its current form. The buildings where they were constructed no longer exist or have been repurposed. The people who designed them have aged or passed away. The computing systems they used are primitive relics compared to current technology, and yet the Voyagers continue, although closer to their final silence every day, with less energy every day, to keep themselves awake in the infinite cold of space. The death of the Voyagers will be silent, but not forgotten. It will represent the end of an era, the closing of a chapter in the history of space exploration. But their physical journey will continue for eons after their functional journey ends. They will float as technological ghosts, unintentional monuments to human ambition, silent reminders that even our most impressive achievements eventually succumb to the passage of time. Energy runs out, signals fade, but the physical momentum endures, carrying them further and further on a journey that never ends, but which they stopped being able to document long ago. There is a beautiful and cruel paradox in the Voyager's destiny. They are in constant motion, moving away from the Sun at speeds that no human will ever experience firsthand, and yet they are trapped as completely as Earth itself. The difference is only a matter of scale and orbital geometry. where Earth traces a nearly perfect circle around the Sun every year. The Voyagers trace extremely elongated hyperbolas that will take tens of thousands of years to traverse. But both, planet and probes, are executing the same fundamental dance, a gravitational orbit around a star. The Voyagers are not escaping. They are orbiting in cosmic slow motion. To fully understand this, we need to think about what an orbit truly means. When we think of orbits, we typically imagine objects moving in closed circles or ellipses, like the planets around the Sun or the Moon around the Earth. But these are only one type of orbit, the bound orbits. Orbits can also be parabolic or hyperbolic, open trajectories, where the object moves away indefinitely, but is still gravitationally influenced by the central body. The Voyagers are on hyperbolic orbits, which means their paths are open and they will not return. But that does not mean they have escaped solar influence. The key is to understand that orbiting does not require circular motion. An orbit is simply the trajectory followed by an object under the influence of gravity. The Voyagers are following the trajectories that solar gravity has dictated to them since the moment they left the giant planets. Every second, gravity calculates their new velocity vector based on their position and mass relative to the Sunday. Every second, the probes respond by imperceptibly adjusting their direction and speed. It is a continuous conversation between mass and motion, an equation that has been solved in real time for almost half a century and will continue to be solved for future eons. But the story becomes even more complex when we consider that the Sun itself is not immobile. Our star orbits the center of the Milky Way at approximately 220 kilometers per second, completing a galactic orbit every 230 million years approximately. As it orbits, the Sun drags along its entire gravitational entourage, the planets, the asteroid belt, the Kuiper belt, the Oort cloud, and yes, the Voyager probes. From a galactic perspective, the Voyagers are not moving away from the Sun in a straight line. They are following a complex helical trajectory, slowly moving outward, while simultaneously orbiting the galactic center along with the Sunday. This dynamic creates a fascinating situation. The Voyagers are bound to the Sun, but the Sun is bound to the galaxy. Therefore, the Voyagers are ultimately orbiting the galactic center as well. They will never escape the Milky Way, even if they somehow manage to completely free themselves from solar gravitational influence, which they will not. They would simply begin to orbit the galactic center independently. The galaxy itself is a prison from which it is impossible to escape, without truly extraordinary velocities, far above what any conceivable technology could achieve. And there is more. The Milky Way belongs to the local group, a cluster of more than 50 gravitationally bound galaxies that includes Andromeda, the Triangulum Galaxy, and dozens of dwarf galaxies. This group, in its entirety, is moving toward the Virgo cluster, attracted by the massive concentration of galaxies in that region of space. It is gravity in layers, attraction within attraction, orbits within orbits. The Voyagers participate in all these movements simultaneously, prisoners not only of the Sun, but of increasingly large gravitational structures that extend across the observable universe. When the Voyagers finally traverse the Oort cloud in 30,000 years, when they are technically outside the region where physical objects orbit the Sun, their velocity with respect to our star will be minimal. The constant gravitational deceleration will have reduced their relative speed to barely a few kilometers per second. At that speed, the gravitational perturbations of nearby passing stars will begin to dominate over the solar attraction. The Voyagers could be slightly deflected, their trajectories curved by distant stellar encounters. But these encounters will not free them. They will simply transfer them from a very elongated solar orbit to more complex galactic orbits. The truth is that the concept of escape is largely illusory in a universe governed by gravity. Everything is orbiting something. Stars orbit galactic centers. Galaxies orbit cluster centers. Clusters participate in the large-scale flows of the universe, attracted toward massive concentrations like the Great Attractor. There is no point where you can be truly free of gravitational influence, where you can float in absolute independence. The universe is an interconnected network of gravitational attractions, and everything it contains is trapped in that network in one way or another. The Voyagers are perpetual prisoners of orbital motion. They will never know true rest. They will never experience complete gravitational independence. They will continue moving for billions of years, long after the Sun becomes a white dwarf, long after Earth is consumed or ejected from the solar system, long after the last light of the last human civilization goes out. They will continue orbiting, following the curves of space-time, dictated by increasingly larger and more distant mass distributions. It is perpetual motion, but not freedom, eternal journey, but not escape. They are prisoners in motion, and they will be forever. On August 25, 2012, NASA made an announcement that captured the world's imagination. Voyager 1 had crossed the heliopause and entered interstellar space, becoming the first human-made object to reach this legendary frontier. The media celebrated the event as the moment humanity finally left its cosmic cradle and took its first true steps toward the stars. Images of the small probe floating in the vastness of deep space became instant icons. It was presented as a triumph of human engineering, an unprecedented achievement in the history of exploration. And it was, without a doubt, but it was also, in a fundamental sense, a deeply misleading narrative. The confusion lies in the term interstellar space. In astronomy, this term has a specific technical meaning that differs significantly from its popular interpretation. When scientists say interstellar space, they are referring to the physical medium that exists between the stars, the dilute gas and dust that fills galactic space. This medium has different properties than the environment inside the heliosphere. Higher density of neutral atoms, higher intensity of galactic cosmic rays, and a magnetic field with a different orientation. Crossing into this medium is significant from a plasma physics and magnetosphere perspective, but it has nothing to do with escaping the gravitational influence of a star. When Voyager 1 crossed the heliopause, its instruments detected dramatic and confirmatory changes. The density of charged particles coming from the Sun dropped precipitously, while the intensity of cosmic rays of galactic origin increased abruptly. The magnetic field changed its orientation, indicating that the probe had entered a region dominated by interstellar magnetic fields rather than solar ones. These changes were real, measurable, and scientifically important. They definitively marked the transition from an environment dominated by the solar wind to one dominated by the interstellar medium. But this transition is purely a matter of plasma composition and magnetic orientation, not of gravitational dominion. The heliopause is essentially the boundary where the pressure of the solar wind is balanced by the pressure of the interstellar medium. The solar wind, that constant stream of charged particles emanating from the Sun, blows outward at supersonic speeds, creating a bubble in the interstellar medium. But eventually, at sufficient distance, the density and pressure of the solar wind decrease to the point where it can no longer maintain its dominion. At that point, the interstellar medium begins to infiltrate, and the heliosphere ends. It is analogous to a wave breaking on a beach. There is a point where the ocean water can no longer maintain its cohesive form and mixes with the sand and coastal water. But crossing that point does not mean you have left the ocean in a broader gravitational or geographical sense. What makes this misunderstanding particularly persistent is that it coincides with powerful popular narratives about exploration and frontiers. We want to believe that we have sent something beyond our neighborhood, that we have truly reached the space between the stars. The term interstellar space evokes images of star travel, of jumping from one solar system to another, of finally breaking the chains that bind us to our sun. But the reality is much more prosaic and, in a way, more humbling. The Voyagers have entered the interstellar medium, but they have not entered the space between star systems in the sense of being free from solar gravitational influence. To be truly interstellar in the gravitational sense, an object would need to be far enough away from all stars that no individual star exerted gravitational dominion over it. It would need to be in a region where the influences of multiple stars balance each other, or where the general galactic tide dominates over individual stellar attractions. For the Voyagers, this point is tens of thousands of years away in the future. Currently, they are in a hybrid zone, bathed by the interstellar medium, but firmly trapped in solar orbits. It is like being in international waters, but still seeing the coast. Technically, you have left the territorial waters, but you have not left the general influence of the Earth. NASA, to be fair, has been careful in its technical communications to distinguish between entering the interstellar medium and escaping the solar system. The scientific documents are precise in their language, specifying exactly what boundary was crossed and what it means. But in the translation to press releases, media headlines, and popular narrative, these distinctions are lost. The public hears interstellar space and understandably concludes that the Voyagers have left the solar system when the reality is much more complex and nuanced. This semantic deception, while not intentional, has real consequences for the public understanding of astronomy and space exploration. It reinforces erroneous ideas about the distant scales involved, about what it means to escape a star, about how far away other stars really are. When we eventually launch missions specifically designed to reach other stars, missions that will require radically more advanced technologies than anything we have today, the public might wonder why it is necessary when the Voyagers are already in interstellar space. The answer, of course, is that being in the interstellar medium and reaching another star are two completely different things, separated by orders of magnitude in distance, time, and required energy. The Voyagers are in interstellar space, but they remain prisoners of the Sunday. They have crossed an important boundary, but not the definitive boundary. It is an extraordinary achievement, worthy of celebration, but we must celebrate it for what it is: the first time human objects have touched the medium between the stars. Not the first time we have escaped the influence of our star. That feat remains, and will likely remain for a long time, firmly in the realm of science fiction. The Voyagers are not alone in their journey toward the darkness of deep space. There are other spacecraft also heading outward, moving away from the Sun on trajectories that will eventually take them beyond the planets, beyond the heliosphere, toward the depths of space. Each has its own story, its own speed, and its own final destination. However, when we examine their trajectories and compare them with the Voyagers, we discover a consistent and unsettling pattern. All share the same fundamental fate of remaining gravitationally bound to the Sun for periods that defy human imagination. None have truly escaped, and none will escape within any time frame relevant to human civilization. Pioneer 10 and Pioneer 11 were the predecessors of the Voyagers, launched in 1972 and 1973, respectively. Pioneer 10 was the first craft to traverse the asteroid belt and to visit Jupiter, paving the way for the more ambitious missions that would follow. Pioneer 11 visited both Jupiter and Saturn, becoming the first craft to observe Saturn's rings up close. Both are now on escape trajectories from the solar system, in the sense that they will not return to the inner planetary regions. But like the Voyagers, they are far from having reached true escape velocities from the solar gravitational perspective. Pioneer 10 travels at approximately 12 kilometers per second and is heading toward the constellation Taurus. If it maintained its current direction, which is unlikely due to gravitational perturbations, it would pass near the star Aldebaran in approximately 2 million years. However, contact with Pioneer 10 was lost in January of 2003, when the probe was approximately 82 astronomical units from the Sunday. It continues to move away in silence, a mute relic of the early days of deep space exploration. Pioneer 11, traveling at similar speeds toward the constellation Scutum, lost contact in November of 1995, at a distance of approximately 40 astronomical units. Both probes will take tens of thousands of years to traverse the Oort cloud, assuming they survive the journey intact. New Horizons, launched in January of 2006, is currently the fastest operational spacecraft we have sent into deep space. It was designed specifically to study Pluto and the Kuiper Belt, a mission it completed brilliantly, with its flyby of Pluto in July of 2015 and subsequently of the Kuiper Belt object Arakoth in January of 2019. New Horizons travels at approximately 16.6 kilometers per second with respect to the Sun, slightly slower than the Voyagers, but still extraordinarily fast by human standards. It is expected to cross the heliopause around the year 2047, becoming the fifth human craft to reach the interstellar medium. But like its predecessors, New Horizons is not truly escaping the solar system. Its speed is insufficient to break the solar gravitational embrace, and like the other probes, it will spend tens of thousands of years traversing the Oort cloud before emerging into truly interstellar space. In gravitational terms, it is heading toward a region of space in the constellation Sagittarius, where eventually, in approximately 800,000 years, it might pass relatively close to the binary star system, Proxima Centauri and Alpha Centauri, although both systems will have significantly changed their positions by then due to galactic motion. There is also a collection of smaller craft and objects that have reached escape velocity from Earth, but that will eventually fall back toward the Sun or remain in solar orbits. The upper stage of the rocket that launched New Horizons, for example, is also on an escape trajectory, although it travels more slowly than the probe itself. Several other objects, from rocket stages to discarded components from previous missions, float in deep space on various trajectories. All share the common fate of remaining gravitationally bound to the Sun for extremely long periods. The fascinating thing about comparing these missions is that all represent the best of our space engineering, and all were launched with speeds that seemed impressive at the time. However, when we put them in the context of the true scales of the solar system and the velocities necessary for a real escape, all turn out to be inadequate by significant factors. It is not a design flaw, it simply reflects the fundamental limitations of chemical propulsion and planetary gravitational assists. Achieving speeds truly sufficient to escape the solar system would require technologies that currently only exist on paper or in our imagination. When we observe the collective fate of all these craft, a clear pattern emerges. All will continue to move away from the Sun for the foreseeable future. All will eventually cross the heliopause, if they have not already. All will traverse the Oort cloud over the next 30,000 to 50,000 years, and all will remain gravitationally bound to the Sun throughout that time, prisoners of a star that refuses to relinquish its control, even at distances where its light is barely distinguishable from the other stars in the sky. It is a humble reminder that sending something into deep space is one thing, but truly freeing it from the gravitational influence of its mother star is something else entirely. The Voyagers, the pioneers, New Horizons, all are heroic explorers who have expanded our knowledge of the cosmos in immeasurable ways, but they are explorers who will never return home, not because they have escaped, but because they are condemned to orbits so elongated that their orbital periods exceed the duration of civilizations. They are prisoners in motion, all of them sharing a common destiny, dictated by the immutable laws of gravitation and the practical limitations of human propulsion technology. Their legacy is not one of escape, but of exploration within the vast, yet definitive, confines of solar gravitational dominion. What does it truly mean to escape? It is a question that seems simple on the surface, but which becomes profoundly complex when we examine it carefully. In our everyday experience, escape means freeing oneself from something, breaking ties, reaching a state of independence. A prisoner escapes from a cell, an animal escapes from a predator, a person escapes from an oppressive situation. In all these cases, there is a definable moment where the escape is achieved, a point where freedom begins. But when we apply this concept to the cosmos, when we try to define what it means to escape the gravitational influence of a star, we discover that the lines blur, the definitions collapse, and we are left with a paradox that defies simple resolution. Gravity, as we have discussed, never completely disappears. It decreases with the square of the distance, but mathematically extends to infinity. This means that technically, even at distances of millions of light years, the Sun still exerts some gravitational force on the Voyagers. It is an infinitesimally small force, completely irrelevant in practical terms, but it exists. So, when can we say that an object has escaped? When the gravitational force drops below a certain arbitrary threshold, when other gravitational forces become dominant, when the object reaches its point of maximum distance and could, in principle, begin to return, if not for other influences. Each definition yields a different answer, and none is completely satisfactory. Let us consider the definition based on orbital energy. We say that an object has escaped when its total orbital energy is positive or zero, which means it has enough kinetic energy to move away indefinitely without returning. According to this criterion, the Voyagers have not escaped because their orbital energy is negative. They are in bound orbits, although extremely elongated. But this definition has its own complications. What happens when other stars begin to exert comparable influences? Do we continue calculating the orbital energy with respect to the Sun, or do we need to consider a more complex frame of reference? At what point does the question of whether an object is bound to the Sun cease to have practical meaning? Then there is the definition based on gravitational dominion. We could say that an object has escaped the solar system when the gravity of other stars becomes stronger than solar gravity. This would occur at some point within or beyond the Oort cloud, depending on the local stellar configuration. But even this definition is problematic. Stars move. The configuration of nearby stars changes over time. An object could be dominated by solar gravity at one moment and by the gravity of another star hundreds of thousands of years later without having fundamentally changed its physical state. Has it escaped the solar system or simply entered a different system? What is the ontological difference between the two situations? There is also a deeper philosophical dimension to this paradox. Escape implies freedom, independence, a state of not being bound. But in a universe where everything exerts gravitational force on everything else, where every particle of matter curves space-time around it, does a state of absolute freedom really exist? The Voyagers might eventually free themselves from the Sun's dominant influence, only to fall under the dominant influence of another star, or the galactic center, or even larger, large-scale structures. No matter how far they travel, they will always be moving through gravitational fields, always following curves in spacetime, dictated by the distribution of mass in the universe. This realization leads us to an even more fundamental question. Is true escape even possible in a universe governed by gravity? Or should we rather think in terms of transitions between different gravitational regimes instead of absolute escape? The Voyagers are transitioning from the dominant solar gravitational regime toward a regime where multiple gravitational influences balance each other, and eventually toward a regime where the galactic tide dominates. But they will never reach a state of complete gravitational independence, a point where no mass in the universe influences them. Such a state does not exist, except in the abstract, infinitely empty space of thought experiments. The paradox deepens when we consider temporal scales. At any given moment, we can measure the Voyager's speed, their distance from the Sun, and calculate whether they are technically bound or not. But these measurements are instantaneous, snapshots of a dynamic process that unfolds over eons. With enough time, the gravitational perturbations of nearby passing stars could alter the Voyager's orbits in unpredictable ways. They could be accelerated, decelerated, or even captured by other stars. Their state of escape or non-escape is not a fixed property, but a condition that evolves over time in ways that depend on future events impossible to accurately predict. Perhaps the resolution of this paradox is not to find a single definition of escape that works in all contexts, but to accept that escape is a contextual and scalar concept. We can say that the Voyagers have escaped the inner solar system, but not the extended solar system. They have escaped the heliosphere, but not solar gravitational influence. They have entered the interstellar medium, but not the truly free space between stars. Each statement is true within its own context, and none completely captures the complexity of the situation. This ambiguity is not a weakness of our understanding, but a reflection of the fundamental nature of the universe. Gravity does not respect clean boundaries. There are no walls, no gates to cross. There is no defined moment where something is inside and then outside. There are only gentle gradients, continuous transitions, influences that fade asymptotically, but never completely disappear. Escape in a gravitational universe is always partial, always relative, always temporal. The Voyagers are not escaping in any absolute sense. They are transitioning between different modes of gravitational captivity, and they will continue to do so for the rest of the universe's existence. Let us now project ourselves toward a future so distant that it defies all human imagination. A future where the cities we know have disappeared under layers of sediment or have been erased by geological processes. A future where the languages we speak are so ancient that no legible record survives. A future where perhaps the human species itself has evolved into something unrecognizable or has disappeared completely. In that future, in approximately 40,000 years, Voyager 1 will pass relatively close to a star called Gliese 445, also known as AC+ 79388, located in the constellation Camelopardalis. It will be the first close stellar encounter of any human-made object. Gliese 445 is a red dwarf, a small, cool star that shines with barely a fraction of the Sun's luminosity. At the moment of closest approach, Voyager 1 will pass about 1.6 light-years away, or about 100,000 astronomical units. It is a distance that seems immense, and it is, but in astronomical terms, it represents a relatively close encounter. To put this into perspective, it is approximately the distance of the outer edge of our Oort cloud. The Voyager will pass near this star at approximately the same distance as some of the outermost objects bound to the Sunday However, even at this close passing distance, the gravitational influence of Gliese 445 on the Voyager will be minimal, insufficient to significantly alter its trajectory or capture it into orbit. Voyager 2 has a similar fate, but headed toward a different region of the sky. In approximately 42,000 years, it will pass near the star Ross 248 in the constellation Andromeda at a distance of approximately 1.7 light-years. Ross 248 is also a red dwarf, slightly more massive than Gliese 445, but equally dim from our terrestrial perspective. The encounter will be similar. Voyager 2 will pass by, too fast and too distant to be captured, but also too slow to truly escape into truly free space between stars. It will simply continue its perpetual drift through the galaxy. It is important to visualize what the Voyagers will be like in that distant moment. Their power generators will have been dead for approximately 38,000 years. No instrument will function. No light will blink in their darkened circuitry. Their antennas will point toward an Earth that will likely have forgotten their existence, if humanity still exists in any form. The golden plates with their greetings will remain attached to the sides of the probes, although cosmic radiation will have slowly begun to degrade the recordings. The aluminum structures will remain intact, protected by the vacuum of space from the oxidation and corrosion processes that destroy objects in planetary atmospheres. The probes will have accumulated microscopic layers of interstellar dust during their 40,000-year journey. Every hydrogen atom, every dust particle they have encountered on their path will have left its mark, slowly eroding the external surfaces at an atomic level. Micrometeorite impacts, although rare in interstellar space, will have created tiny craters on the metallic surfaces. The Voyagers will bear the scars of their journey, a physical record of decades of exposure to the dangers of deep space. However, structurally, they will remain recognizable, preserved by the near-perfect vacuum that surrounds them. From the perspective of any civilization on Gliese 445 or Ross 248, if such civilizations exist, the Voyagers will be nearly impossible to detect. They are small, cold, non-reflective objects beyond their faint natural albedo, traveling through the vast darkness. Without active transmitters, without significant heat emissions, they will be essentially invisible against the backdrop of space. The probability of them being discovered by alien observers is astronomically low. They will pass unnoticed, technological ghosts silently floating through star systems that will never know of their passing. After these first stellar encounters, the Voyagers will continue their journey for millions of years more, passing near other stars in the distant future. Each encounter will be similar, an approach that would seem close from our terrestrial perspective, but which in practical terms represents distances so vast that no significant interaction will occur. The probes will follow trajectories determined by the changing gravitational configuration of the solar neighborhood, their paths slowly curving in response to the masses distributed across this region of the galaxy. They will orbit the galactic center, along with the stars they encounter, participating in the grand gravitational ballet of the Milky Way. On timescales of hundreds of millions of years, the Voyager's galactic orbits will carry them through different spiral arms, expose them to different densities of interstellar matter, and subject them to occasional encounters with giant molecular clouds and star clusters. Eventually, in billions of years, when the Sun becomes a red giant and then a white dwarf, the Voyagers will continue orbiting the galaxy, completely disconnected from the system that created them. They will be relics of an extinct star, unintentional monuments to a civilization that will likely have disappeared eons ago. Their journey will have no definable end, only a perpetual continuation through the vastness of space and time. silent witnesses to cosmic evolution unfolding over periods that make the current age of the universe seem like a mere blink. We have reached the end of this conceptual journey, having explored the multiple layers of truth surrounding the Voyager mission. We have carefully dismantled the popular narrative, examined the relentless mathematics of gravitation, and confronted the timescales that defy all intuitive human comprehension. And now, in this moment of final reflection, we must ask ourselves, what does all this really mean? What does it tell us about our place in the cosmos, about our ambitions as a species, about the very nature of exploration? When we confront the physical realities of the universe, the answer is not simple or completely satisfactory, but it is deeply illuminating about the human condition and our perpetual desire to reach beyond our grasp. The Voyagers have not escaped the solar system, and they probably never will in any meaningful gravitational sense. They will spend 30,000 years traversing the Oort cloud, remaining under the Sun's gravitational dominion all that time. Even afterward, when they finally emerge into the space where the influences of multiple stars balance each other, they will remain prisoners of increasingly large gravitational structures. First, the solar neighborhood, then the galactic spiral arm, finally, the galaxy itself. The cage expands, but it never completely disappears. And yet, this reality does not diminish in the slightest the profound meaning of what these probes represent and have achieved, because the Voyager's true achievement does not lie in escaping, but in trying. It is not in breaking chains that prove to be impossible to break with our current technology, but in extending those chains farther than any human object had gone before. The Voyagers are monuments to human audacity, to our capacity to build artifacts that will outlive civilizations, to our insatiable desire to touch what seems untouchable. That they remain gravitationally bound to the Sun does not make them less extraordinary. It makes them more poignant, humble reminders that even our greatest technological achievements are small compared to the forces that govern the cosmos. There is a melancholy beauty in this reality. The Voyagers will continue their journey for eons, long after everything we know has disappeared. They will float silently through the Oort cloud. They will pass near distant stars. They will orbit the galactic center for billions of years. They carry with them the sounds of Earth, images of human beings, greetings in languages that will likely be extinct long before the probes reach their first stellar encounter. They are time capsules that no one will probably ever find, messages in bottles thrown into an ocean so vast that the probability of discovery is essentially zero. And yet we sent them, because the very act of sending, of trying, of reaching out, is fundamentally human. The question of escape has led us to confront uncomfortable truths about the scales of the universe and the limitations of our technology. We have learned that interstellar distances are not just great, but incomprehensibly vast, that the velocities necessary for true interstellar travel far exceed what chemical propulsion can achieve, that the time necessary to traverse even our own solar system exceeds the duration of recorded human history. These are humbling lessons, reminders that we are a young species in an ancient universe, barely beginning to understand the true scales of time and space that define cosmic reality. But these lessons should not lead us to despair or nihilism. Rather, they should inspire us to think beyond, to dream bigger, to recognize that truly significant challenges require solutions that we have not yet imagined. The Voyagers were built with 1970s technology, launched with chemical rockets, accelerated by fortuitous gravitational encounters with planets that aligned by pure orbital chance. They are engineering marvels for their time, but they represent only the first tentative steps of a species just beginning its exploration of the cosmos. The true interstellar craft, when we finally build them, will require radically different technologies. Perhaps laser-driven solar sails, fusion drives, or concepts we have yet to conceive. The Voyagers teach us something fundamental about the nature of exploration. It is not just about reaching destinations, but about the journey itself, the knowledge acquired along the way, expanding our horizons even when we confront seemingly insurmountable limits. They teach us patience, because the cosmos operates on timescales that make human haste irrelevant. They teach us humility, because even our most impressive achievements are minuscule compared to the forces and distances that govern the universe. And they teach us perseverance, because the fact that something is extraordinarily difficult does not mean it is not worth trying. So, as the Voyagers continue their eternal journey, trapped in their invisible gravitational cage, but moving tirelessly forward, we must recognize them for what they truly are. Not successful escapists, but brave explorers. Not liberated, but perpetually in transit. Not free, but gloriously persistent in their unending voyage. They are our ambassadors to eternity, carrying a message not so much for alien civilizations that will likely never find them, but for ourselves, that we are a species that looks up, that asks, that explores, that never stops trying to reach the stars, even when the stars remain frustratingly and beautifully out of reach. If this journey through the boundaries of the solar system and the realities of cosmic escape has fascinated you as much as it has fascinated us, I invite you to subscribe to Ciencia Nocturna. We will continue exploring together the deepest mysteries of the universe, unraveling the hidden truths behind popular narratives and discovering that reality is always more complex, more fascinating, and more beautiful than our simplifications suggest. The Voyagers will continue their silent journey, and we will continue ours, seeking to understand, explore, and marvel at the immensity that surrounds us. Good night, and may your dreams be filled with distant stars and unanswered questions.